All right. Well, this is going to be an interesting thing to get started with, so we will see how it goes. I will talk more about how we're going to adjust things in terms of getting grading done a little bit later on. Uh, what we will end up doing, I want you somewhere between later today, this being Tuesday, through this upcoming Thursday. So just those 3 days. Please give me an idea of what times you have available. Probably in the evening is going to be better for more people than others, but let me know which days and time periods will end up working for you, where we could try to get a common 2 hour block, and then we'll end up having our exam. The way the exam will be done, I'm going to end up having it done through sapling learning. The other side of that is, as far as the sapling learning goes, uh, the I'll end up having you to uh, I'll whenever you end up when you end up doing the exam, you will be allowed to use your book. You'll be allowed to use your notes, largely because there's not a darn thing I could do about it if you tried to anyway. And so, but I also will let you know I'm not going to end up giving you the evil, difficult thing that I otherwise would do. So these will end up being problems that are not the ones you've done, but will be problems that sapling that would be associated with sapling. So we'll deal with that when the time comes. So again, there's no new material, so you have a little tiny bit of extra time to look at that. So I'm hoping to get that done by next Tuesday. So somewhere, get that done. I don't mind doing it on the weekend, by the way. So if some of you would prefer, you end up saying that weekends work well for you, let me know. So I want to end up being flexible. The final exam, on the other hand, it has to be, yea, verily, it will be done in that time period. And that will, it will be multiple choice. Exactly which kind of multiple choice thing it is, I hope I'll be able to actually use my traditional final exam for that. So we'll stay tuned on that, and we'll see how that works. So, like I said, I, I personally am very weirded out by all the stuff, and I am trying to end up being supportive of you being in that same boat. From now on, what I will end up doing, all of my old office hours, I will be available so that we can end up doing a voice chat um, over Microsoft Teams. Just pop me an email, and I'll have that open all the time. And if you want to end up talking to me, if it's during the office hours, I mean, of course, there may be somebody ahead of you in queue, but as long as there's nobody ahead of you, you can end up, talking to me that way. I also will do all of these things asynchronously, so for the same reason, I will also be available for the same kind of thing for online chat over Teams. We can end up doing that during the regular class time, so 8 to 9:15s on Tuesdays and Thursdays. You'll be able to do that too. So that is at least the overall picture on that. As far as quizzes go, I will see if I can make Georgia View work with those. I don't know if I will, and if I can't, it's not your fault. And if it's not your fault, you don't get harmed for it. So I'll end up basically, if it's not possible for me to do it, and I tried to put one in and it is gone. It just went away. I don't know why it went away. It said it was there and it's not. So I don't know how Georgia View stuff works. I've avoided it as much as possible. So that's where we're at. Okay, so we'll play that a little bit by ear too. Okay, so and as far as homework goes, I'll end up assigning homework due next week for the stuff that would be this week's material. I'll try to break the lecture stuff up into little smaller bits so that you can end up. So this will be your first one, but we'll end up looking at more of this in smaller chunks. So maybe it will be easier for you to do. And of course, you can also, of course, it's recorded, so you can go back and reread it too. I have lecture notes in there, which is intended to follow along with what I'll be doing. Hand wrote those, and if you if you can't read my handwriting, you can ask me questions on that, on text chat, or of course you can email me too. So anyway, that's where we're at. All right, so now that we got all that weirdness out of the way, we'll now end up doing some stuff where we're introducing new material. But before we do that, there's also some stuff that we end up needing to do in terms of just understanding some geometry stuff. Because if I was standing in front of the classroom, then geometry is pretty much, there's no ambiguity. Here, I do want to end up describing what I mean. So if I end up saying, and this is going to be a little challenging for me because the camera makes these backwards. So if I point that way, it will end up meaning to the right. So that direction is what I mean to the right. That direction is to the left. And whenever I end up saying into the screen, that will be this direction. And out of the screen will be that direction. And then up will be that way, and down will be that way. So hopefully this will end up being comprehensible. But again, you can go back and check what I mean by that. One other thing that's strange is because the camera reverses all these directions, I'm going to have some difficulty doing this stuff logistically. So we'll try to make that happen. Okay. All right. So what we're going to start with in terms of looking at induction, we want to imagine we end up having and we'll pretend like this pen is a piece of just a metal bar, nothing special about the metal bar. And that what we're going to end up having with this metal bar, we're going to end up having a magnetic field that's pointing out of the screen this way, all around. So it's you're pointing in that direction. And I'm going to end up having this thing, and I'm going to end up having to move it to the right at a constant speed. So it's moving at constant speed this way. So if that happens, the thing to understand is the charge carriers that are inside this will have an average velocity that goes the same direction as the bulk object will. And the reason for that is if it didn't, then all the charge stuff would be left behind or jump out ahead of it. And so we know it's not splitting apart as I move it. So the charges still have to be inside this area, which means that they have to move at the same average velocity as the bulk object does. So for that reason, we can end up characterizing then, in this situation, what my amount of my magnetic force will be acting on this rod. So my velocity is going in this direction. So if we consider what happens with a positive charge, that my charge times my velocity plus times that direction is that direction, so QV is that direction, and my magnetic field is pointed in this direction going into the screen. So to end up finding the direction of my magnetic force, it's QV, right? QV cross B, right? So that's going to be pointing up. So my magnetic force on a positive charge will be going in this direction. Similarly, whenever I have a negative charge, then my QV points in that direction, and I curl it that direction going into the screen. So, this direction. Then I end up curling it that way, which is into the screen. So my magnetic force will be down. So I end up having a magnetic force on a positive charge when it's moving that way. Now, if it's not moving, I don't have one. But if it's moving that way, I'll end up having positive charge with a net force that direction, negative charge with a net force that direction. So starting from a rest position, then you'd end up starting to build up positive charges going up and negative charges going down, and I dropped my pen. So like I said, this is the first go with this. So we build up positive charges up here, negative charges down there. But if that was the only force that acts on it, it would just keep on going, and these keep on going, which of course it's not going to do either. We said it's going to stay inside the bar. And the reason it stays inside the bar is that if I end up having positive charges that get deflected up here, I've got negative charges down here, then these positive charges that build up here are attracted to the negative charge down there. And the attraction is through an electric field. So I end up inducing an electric field from motion of an object through a magnetic field. So this is what we're talking about when we deal with the idea of induction. We end up producing an electric field from a magnetic field. So in order to be able to describe how much this will be, we'll end up thinking about what the magnetic force is. And the electric force has to exactly match. The reason why it has to match is if it did, it would accelerate out. And again, it would either fly out of it or it would, it would cancel out. Neither one of these is going to happen. It's going to build up positive charge up here, build up negative charge down there. So they have to end up being in balance. So my magnetic field could end up being exactly that way, but it could end up being in part that way and in part, be at an angle instead of being like this. So I want to end up allowing for that as a possibility. So if my velocity is this way, my magnetic field was back that way, then my cross product, of course, is going to be Q times my V times my magnetic field this way times the angle between those two, right? The sine of that angle. So that ends up giving my magnetic force. And my electric force, of course, Q times E. Those have to be the same magnitude, so that ends up through the derivation that you see in the text that I wrote. That ends up giving me that my electric field that's induced will end up being the speed of it times the magnetic field magnitude times the sine of the angle between the velocity and the magnetic field. And we'll have to be really careful with which angle we're talking about because that's going to come up a little bit later. All right, so the next thing we want to do, we've got an electric field, and notice it's got to be the same value all the way through, because if it wasn't, again, you'd end up having it move one way or the other. And we're getting, in this situation, to a steady state. It's not equilibrium exactly, because remember we said at equilibrium you have no electric field inside a conductor. It's not equilibrium, but it is steady state. Nothing is changing after that fact. But notice if I stop it, then all of a sudden these things go back and the charges redistribute to being no charge at all. So it's induced in that sense. All right, so the next thing to understand is that because my electric field is uniform all the way through here, I also will have a potential difference. And to find potential difference, you'll remember we ended up saying it was minus the definite integral of the definite line integral of my electric field over the length of this. So to end up finding it, my electric field, my electric field is pointing, this is positive, this is negative, so my electric field was pointing this way. But if I'm looking for my change in potential, because my potential is positive up here, negative down there, my potential this would be the opposite direction of the potential. So if I calculate a potential difference, it will end up being my electric field times my length times cosine of the angle, which is 180 degrees. There's a minus sign in the definition, minus the line integral. So that minus and the minus due to the opposite directions of those give me my potential differences being the magnitude of my electric field, which I already just calculated, times the length. And I'll call this length L, the length of my rod. And what we usually do is to end up calling the length, calling the potential difference here an EMF rather than calling it a potential difference. It's still volts. It basically means the same thing, but that's just the way that it's normally done. So that will end. So we've gotten then our formula for my potential difference, which is my EMF. That will be my speed times the magnetic field times the length times the sine of the angle, remember, between the velocity and the magnetic field. And that will end up being the end of this first piece.